Hello, in this video, I'm going to show you how to use the GeoAI Python package step by step. Whether you are new to GeoAI or you have used some other Python packages for GeoAI, you are frustrated with the complexity of those packages, this video is going to be very helpful for you. So I'm going to show you step by step how to install the package and how to get started very easily. You can use the Python package to easily detect any object you want from satellite imagery using some of your own data, or you can use pre-trained models. Super easy. So this is what it looks like. Imagine you might have some satellite imagery or aerial imagery, and you have some like building footprint, or it can be any object, so it doesn't really matter. It's basically any object you want to detect. As long as you have some data, you have some label, then we can do it easily. So this will be the input to our model. You can see this is just the building footprint, and we can use that to detect some of the new buildings, or some the building have changed due to, for example, natural disasters, and we can easily apply that to detect the new buildings or the missing building. So this is what the final, for example, the output looks like. So we can easily detect our own buildings, apply the techniques to a new area, and this is what the outcome looks like. Of course, it's not perfect. I only train for a couple epochs, but you can train the model for a longer time to get much better result. But this is just with couple lines code, less than 5 minutes, you'll be able to get something like this. For your own data, you can certainly run this one, reproduce the result that I'm going to show you here in this video. But like I said, you can adapt this one to do any object detection. It can be buildings, it can be trees, it can be swimming pools or solar panels or anything like that. And we're also going to show you how to evaluate the performance of the model. Very, very easy to get started. So in order to follow this tutorial, we need to download the notebook example. So you can go to the opengeoai.org website. So this is a new Python package I created a couple months ago, and I've added a lot of functionality, also provide a lot of tutorials. You can go to the website, you can see a lot of examples in here, and you might be overwhelmed by this, so many examples. So this video is just to get you started. I'm going to show you the common workflow, and once you are familiar with the workflow, you can try out some other tutorials. And so the one that we're going to utilize is this one here, train segmentation model. So just click this one, and then it's going to open the notebook on the web page. There are two ways you can run GeoAI or run Python. You can either run it in the cloud, or you can run it locally. In the cloud, I would recommend using Google Colab because it's free. It also has GPU, so 16 gigabytes, so you can test it before if you don't have a GPU on your computer. But if you have a GPU on computer, then I would recommend that you install the package. So I'm going to show you two ways. The easiest way would be just to right click and then just open a new tab. So you open this one in Google Colab, and that's it. One thing you need to keep in mind is you need to make sure that you switch to the GPU runtime. Otherwise, it's going to be pretty slow when you're running the models. And so what you need to do is to go to the runtime, and then from here click this change runtime type and switch to T for GPU and click save, and that's it. So now we have access to the GPU runtime. So all you need to do is to go to the first code block to install the GeoAI Python package. You can either press Ctrl/ on your keyboard to remove the hashtag, or you can come here and then remove it manually. And so if you have the hashtag, that means it's a comma, it's not going to be executed. So once you remove that, then I can just click this one, run anyway. Then you will be able to run and install the packages. So this is going to take a couple minutes because you're going to install a lot of dependencies. Also, you're going to install the Conda and also NVIDIA and GPU. So it might take a couple minutes. Just be patient. Once it's finished installation, then you will be able to run through the code blocks and then one by one. I'm going to show you in Jupyter Lab. So this is how to install the package on Google Colab. But if you have a GPU, you want to try it on a local computer or on some high performance computers, then you can install this one to the environment where you're working on, and you can click the link to the installation page. And from here, you're going to show the instruction. The recommended way is to use Conda or use Mamba to install, because the package has been pre-compiled, so you're less likely going to run into installation issues. But if you don't have that, you can use UV or use pip to install. So for this tutorial, I'm going to show you how to use Conda. In order to use Conda, you need to have maybe mini Conda or Anaconda install. If you don't know about that, you can just search Google it, mini Conda, and then just copy and then paste to the browser. Then you should be able to find the website to Conda, and then from here you can click the link to install. For example, here, quick install page, and you're going to find instructions for different operating systems, Windows, Mac, or Linux. You can just copy this command line and then just paste to your computer terminal. Then you'll be able to install the package. So this kind of a very standard process to install the package. And once you have install mini Conda, then you're going to have the Conda command available. If on Windows, you can go to the Start menu and then go to the Anaconda menu. Then you're going to open the Anaconda prompt. Because I'm on Linux, so I don't really have the menus to show you. But if you're using Mac, it should be pretty much similar. So all you need to do is just to open your terminal, and then you can just type the Conda command. If you can see the Conda, the output, that means your Conda has been successfully installed. And once you have that, you can just Conda create. Let me zoom in here. Conda, let me just maybe clear the output first. Okay, so Conda create this end, and then you can give a name to your Conda environment. I can just say maybe GeoAI, and then Python, whatever Python version. I support from 3.10 all the way through 3.13. To be safe, I usually recommend one version lower than the latest one. So right now the latest version is 3.13. I'm going to install 3.12, and that's it. Well, I already have one. Maybe let me try another one. So maybe I can say no. I can change the name. So maybe just AI. Okay. If you don't have the name conflict, you can use whatever you want. Okay. So it's going to ask you to whether you want to install all the packages, and you just click yes, or you can just hit enter Y. Then it's going to install all the packages. This might take a couple minutes, depends on your internet, because I have installed some of the packages before. It has the cache on my computer, so it's not going to re-download them and re-download them. So that's why it's pretty fast. And then just Conda activate AI. So you're going to activate this Conda environment. And once you have that, you can use Conda to install the GeoAI package. So what you need to do, if you don't know, you can go to the GeoAI website. Again, the link is in the video description below. So all you need to do is just copy this line, Conda install C, it means the channel. So I'm going to install GeoAI from the Conda for channel. So you just say Control C and then come back to here, Control V, hit enter, and that's it. So this is going to take a couple minutes, because it's going to basically figure out all the dependencies that it needs to install, and also make sure there's no dependency conflict. And once it's finished installation, then you'll be able to use, you can just start Jupyter Lab, and then you'll be able to start using it. So for example, here right now, it doesn't, it's still running. So to save some time, I'm just going to use my previous environment. So Conda activate Geo. Okay, so once you activate the Conda environment, and you can just type Jupyter Lab. Okay, then just hit enter. You can go to open Jupyter Lab in your browser. Then you can start doing coding, and you can start importing GeoAI or something like that. So this is kind of a simple process how to install the package locally. Like I said, if you don't have a GPU, the better, easier way is to use Google Colab. So this one shows you here, we already finished installation. There are no error or anything, so it's great. And I'm going to just clear the selected output. And once you've clear the output, then I can start click this one, import GeoAI. If you don't have any error message, then that's a good sign. So then you can follow step by step, just run the code block one by one. You will be able to get the result. But I mean, in general, the Google Colab, the performance is a little bit slow. It's going to be a little bit slower compared to the same GPU on your local computer, because it's kind of a shared resources. But it's free, so if this at least backup if you don't have GPU resources. Okay, so after that, I'm going to basically start from my using my local Jupyter lab because it's going to be much faster. Okay, I have loaded up the notebook on my local Jupyter lab. So next, I'm going to show you step by step how to do deep learning with the GeoAI package. So once you open on the left side here, there's a navigation bar, so you can see the table of content. This is a document that has multiple sections, so you can navigate to go to different sections. So the first step you need to do is to import the package. Assume that you have already installed it on a local computer or you already installed it using Google Colab. So just press Control Enter. It's going to execute this one, or you can press Shift Enter. It's going to execute and then go to the next code block, or you can press Alt Enter, then it's going to execute and then generate a new code block. So those are the three keyboard shortcuts that you might want to be familiar if you're using Jupyter Notebook environments regularly. Once you import the library, then the next step is to download some sample data. My recommendation is to run these notebook examples using the sample data that I provided, because I have tested it. It makes sure that it works. And once you figure out the workflow, you can customize that to your own data. It's pretty simple. So we have 3 data sets here. I have a raster data set, basically is the satellite imagery for training, and also I have a vector data, basically the building polygons. I also have another one on raster, and so that's it. You have 3 data sets, one for training, one for label, and then one for the testing. Once you have that, you can just run this code block. It's going to pointing to the sample files hosting on Hugging Face. Then you can use the GeoAI download file function to download all the 3 files all at once. I have already downloaded it before, so it's pretty quick. But for you, it might take a couple seconds to download the file, depends on your internet speed. Once you have downloaded the file, then we can print out some sample data information. So I can just use the get raster info function to get all the raster. So as you can see from here, this is a 3-band RGB imagery. Actually, it's area imagery from USDA, so National Agriculture Imagery Program. I think it's 60 centimeter resolution, so you can see from here 0.6. So also you can see from the resolution here 0.6. That means it's 60 centimeter resolution is pretty high. And also you can see the bounding boxes, the min, max, mean, standard deviation, something like that. So if you sometimes you just want to get a basic information about the imagery, you can open it in desktop.js, or you can just use GeoAI to get raster info function to quickly get the metadata information. You don't necessarily have to do this. You can directly go to the GeoAI, but I'm just showing you some of the utility functions that if you want to see some of the metadata, this can be helpful. So get raster info. Also, you can use the view vector interactive. So this one allows you to overlay the vector data on top of the raster. So just run this one. Should be pretty quick. Okay, so now we have this data set here, and you can zoom in. It should be able to load up the raster file. It's not loading up. Let me see here. Interesting. One again. Oh, I think it's right now raster URL. Probably earlier I changed it to raster path. Okay, it comes up. So basically, the background can be either your local raster, or you can point to a cloud optimized GeoTIFF available through HTTP URL. And so this is basically the input data we have. It's 60 centimeter area imagery, and also the building polygons. I downloaded from our tour maps. It's all free, open access. So this is the 2 data set we have. Then what we need to do is to actually create the training data. Also, you can build the raster imagery as well. So this one basically shows, oops. I think something is wrong with my notebook. Anyway, don't worry about that. You can run it, or it's just for visualization only. Once you have the data, we can create the training image tips. So for deep learning, we don't directly fill the entire satellite imagery into the model, because sometimes the imagery can be pretty big. So you want to basically subdivide the images into smaller pieces, and then you're going to feed a bunch of pieces into the model one by one until you finish all the pieces. Because you don't want to feed gigabytes of data all at once. Your GPU is not going to be able to handle that. So that's why we need to basically specify an output folder, then just call this function export GeoTIFF tiles, Then so the input will be the area imagery where we're going to output, and also the in-class data. That means it can be a raster or it can be a vector, so it's very flexible and depends on the input data. So if it's just a raster mask, you can just point to the geotiff, that's fine as well. And also the tile size is like the image chips, how big you want the image to be. So this is 512 by 512. And also the stripe basically means the overlap, right? So it's going to moving from the left to the right. So 512, and then you move to 56 pixels. That means it basically 50% overlap. So we do need to have the overlap, because otherwise you're going to have the when you do the detection, the edge is going to have artifact. So you have the overlap. Then when you detect the features, you can merge them. So it's going to be so much better. And the last one is about radius. So for buildings, we don't really need set a bar for radius, but if you are trying to detect linear features, for example, rows or network or something like that, and if your vector data is just a single line, then you need to set a bar for radius. Otherwise, it's going to be just 1 pixel. So sometimes the line might get disconnected, and it's going to not look very good. But like I said, it depends on your use case. For this one, for the buildings, we don't really need that. So that's why we set this one to 0. And as you can see, it's going to actually subdivide the images into different image chips. So here you can see in total we have 36 image chips. So basically going from the left to the right, from the top to bottom, and it's going to have 50% overlap with the moving window. And so in total we have 36, because so basically what it does is the image width divided by the size, image height divided by the size. So we basically count how many of those, and it's also going to show you, for example, okay, this is the dimension here, like divided by 512, and you get pretty much how many rows and how many columns, right? 36 by 36, in total 36 tiles. So it can be something like 6 tiles horizontally and then 6 tiles vertically. So total we have 36. And if you want, you can open here left side, so the buildings. So this is basically where the images are being saved to. So you have the image directory, and these are all the image tiles that have been generated. You also going to have the corresponding labels. So under the hood, the vector polygons, building polygons, has been converted to raster, basically vector to raster, and then just match the raster with the area imagery, and then you're going to basically subdivide them. So you have one-to-one relationship. Each pixel of the area imagery has a binary mask 1 and 0. So, and you don't have to worry about that. It's all automated, so it's pretty straightforward. So that's it. So basically specify your input data, and then just create the image chips. Then we can start training the model. So this is something that if you look what's other tutorials, sometimes it can get quite complicated because there are a lot of technical terms. But I have simplified the package to make it really easy to use and understand. So basically what you need to do is figure out some of the input data, and then you can specify some of the model you want to use. If you want to learn more, you can check out this link here to take you to the segmentation, the Python segmentation models. So this one has a lot of models available, and also pre-trained weights. So in that way, we don't have to train from scratch, because it has been trained on a lot of popular data sets, and it has a lot of model architecture and also pre-trained weights. If you're new, like you don't really understand exactly like what's the architecture, so you can think about the architecture basically from the input to the output. So in between, there are a lot of steps, and the architecture is like design all the steps like within the whole process. And there's another one called encoder. So encoder essentially is from the input, it's going to turn your input into some kind of numbers, numerical numbers, because the model doesn't really understand 0 and 1. It only understand 0 and 1, and then so every deep learning model eventually going to turn either its images, video, text, whatever, turn into numbers 0 and 1. So the encoder basically is going to you can see turn into numbers and extract some core features from the data. So we're going to basically abstract the data. So you think about the encoder is going to provide inputs. One of the key steps in the architecture from the input to the output. For the output, you're going to have the decoder. Basically means after the model has run through the data, it's going to generate some numbers. So you're going to turn the number into some classification. For example, it's building going to have 0 and 1. So you don't have to understand, you don't have to worry about all the technical terms, don't worry. But you can think about, okay, I have some data, I want to do deep learning and give a model. So the model can be some pre-trained models, or you can train the model from scratch. And the model can be, there are different options. Just like you can use ChatGPT, you can use Gemini, you can use Grok. There are so many models out there. So if your task is to find some answers, you don't really care about which model. Of course, there are some variations. The performance might be different, but you can try each one. The workflows will be pretty much similar. So what we're going to do here is to try two different segmentation models. One is called UNet, the other one is called SegFormer, and the function is pretty easy and straightforward. So GeoAI to train segmentation models. That's it. You don't have to worry about how to construct the model architecture yourself. You can focus more on the data. So the images is where earlier we already generate the image tile. So this is basically the image folder that we have the buildings, right? And then the images directory is where we have all the image tiles and also the corresponding labels. So all we need to do is to basically just specify this input, and then you can also specify the output where you want to save the UNet models. And the other three key parameters is the architecture. As I mentioned, there are different type of architectures here. For image detection, you can just simply use UNet, or you can try out different architectures here. So just replace the name. And then for the encoder is the one that used to turn your images into numerical numbers and then extract the features from the imagery. So for the encoder, there are also different type of options in here. And if you want to see more options, you're welcome to go to the Python segmentation website. And from here, you can click the available encoders and look at here. There are some of these options available. You can read it to learn more. Also, there's a table showing you all the encoder and also the pre-trained weights. ImageNet, for example, is a very popular one. That means the encoder has been trained on that data set. They are not necessarily geospatial data. It can be just some photos or something like that, but it already trained on the model, so you learn some of the patterns of those imagery, edges, circle, something like that, and we can just use this one to as the pre-trained weight. Then you can fine-tune the model using our geospatial data. So that's the whole point of using the pre-trained weight, because it's going to converge much faster. All right, and so besides that, you can also specify the number of channels, right? So you have an imagery. Right now we're using the area imagery just RGB, but you can replace your input data with set imagery, Landsat, Sentinel, whatever set, or even hyperspectral, right? So depends on how many spectral bands that your data have. You want to change this number of channels to the number that you want to do, right? So you can have RGB, or you can have 4 with the near infrared band or something like that. So you change this one. So not just RGB, it can be 3, it can 5, 10, depends on your input data. And the number of classes is how many classes in your what you're going to detect. So we only have buildings and then non-building. So the background and the foreground. So the class is going to be just 2. But you have more classes, then you can change the number of classes to whatever number of classes you want to detect. And the batch size is basically, earlier we already said 512 by 512. So the batch size is like at one time how many images you want to fit into the model. So this is going to depend on the GPU size. If you have a larger GPU, you can fit more, make the batch size larger, you can fit more images all at once, but it's going to be a little bit slower. So you can try 4, 6, 8, right? Whatever number you can try it out. So it depends on the GPU. So 8, you can try with it. And the number of epochs is, let me run this one because it's going to take a couple minutes. So the number of epoch is because you have 36 image tiles, right? So for each time, think about here, batch size is 8. 36 divided by 8 is like about 4.5. So that means you're going to take 5 batches to finish one epoch. That means one epoch means you go through all the images tiles in your input data. So as I said, this one we have 36. So that means it's going to 4.5 times. And going to finish, and that's called one epoch. So the number of epoch means like how many times like you want to go through them entirely, right? Number of 20 epochs, that means you're going to run 20 times, 20 times. So the more usually the better, but you don't need to have too many, because sometimes like after 10, 20 epochs, the model already converts. So you already get pretty high accuracy, then you don't need to train too many epochs. But in general, as a rule of thumb, you want to have at least 10, 20, or maybe 50. But you can evaluate the performance matrix. I can show you later. So if you already have pretty accuracy, then you don't need to train too many. Learning rate is basically like when the model is doing the training, you need to adjust all the parameters. So the parameters is like the learning rate. Do you want to learn faster? Sometimes you might go too fast, or do you want to go very slow, but it might take forever for you to compose. So this is usually set as 0.01 or 0.01 or something like that. You can use the default settings. You don't really need to worry about that. And the val split, that means validation split. So 0.2 means we're going to use 80% for training, 20% for validation. So this is kind of the norm, usually what we do, because if you don't have the validation, your model is going to be overfit. Overfitted, that means when you apply to real data, it might not perform really well. So you always need to have some data left for doing the validation. And that's pretty much it. The last one, verbose equal to true, is whether you want to print out some of the output. So this is what the model looks like. I'm going to go through all the process. I'm going to show you, okay, I'm going to use the CUDA to train the model, and then in total, how many images? 28 for training, and then 8 for validation, and then the size. Also, because I have 2 GPUs, so we're going to use 2 GPU for training, and we're going to use the UNet architecture, ResNet 34. That's it. And this model has 24 million parameters. And then you're going to start going through each epoch, right? So in epoch 1, we have total 20, so base size about 1 to 4, right? So we're going to show you, like as I mentioned earlier, so you're going to have at least, I think, 5 epochs. So 1 to 5. Also going to show you the training loss and also the validation loss. So this is the one that you do want to pay attention. So the overall trend you want to see is that the IOU should be increasing, the loss should be decreasing, IOU and also the dice score, so basically the F1 score should be increasing. If you look at the number here, it looks pretty good, right? So after 20 epochs, we already have 0.91, basically 91% IOU, so it's pretty high. The validation score, the dice score, basically the F1 is 0.95, is even higher. So this is a good sign. That means the model is performing pretty well. And of course, you can try a different model. Everything else remains the same, except that right now we are using the SegFormer and also ResNet 152. That means it's a different model, so the model architecture is different, and this one has 59 million parameters. That means it's a much larger model. You're going to take a little bit slower because the size is much larger. So if you don't have a larger GPU, sometimes this one might be pretty slow. So usually you want to try the smaller model first, and then you can slowly change to a larger model if you have the GPU to run it. So, and similar to the UNet model, this one is also performing pretty well, right? Just with 2 to 3 epochs, with the accuracy increased from 50% all the way to 74%. The reason why you get 50% at the beginning is because of the pre-trained weight. So because we use the ImageNet pre-trained weight, otherwise you're going to take a longer time to converge because you don't have the pre-trained weight. It's going to be random. So we're going to figure out like what weight going to be suitable for the model. And that's it. So as you can see, it takes only couple seconds for me to train the model. And once the model is finished training, then you're going to find the output. So you can see we have these two directory here, UNet models and also SegFormer models. So inside you'll be able to find a couple files here. Base model, basically the one with the highest accuracy, basically the highest IOU. And also the final model is the one that's the last one. So as you can see from here, Sometimes the last model may not necessarily be the best one, because when it's adjusting the parameter, it's kind of random. So sometimes the result might get worse. So usually what you want is to use the base model, and also you have the training history, the one that we can use to plot, do the validation. And so I have a code block actually at the bottom here. You can actually go to this bottom one. You can take a look at it first. So we can just run this one, and I'm going to show you, like, this is the loss and this is the IOU. So in general, you're going to see the IOU and also the F1 score increasing. So this is exactly what we're expecting. If the IOU is decreasing or is fluctuating, means your model is actually not performing very well. Then you might need to try something else. Look into your data, see if there's any data quality issues. All right, so this is how you train the model and then evaluate performance. As I mentioned, there's only a couple steps, right? Specify input data, create the image tiles, and then train the model and then evaluate, right? So 4 steps. And the last step is to actually run the inference. So run inference, that means we're going to apply our train model on a new imagery. So we're going to run this one. So I'm going to save this one, the result to here. So just run this code block and then call this function semantic segmentation. Then you can provide the input. Okay, so this is the imagery. I'm going to test it on, and this is where I'm going to output. And also the model path is we are using the base model as I mentioned. You're also welcome to try the final model if you want to, but using the base model, I'm going to give you the best result. And lastly, this is what you want to do, because if your model is trained on UNet, you want to do the segmentation using the UNet architecture as well. The encoder, we also use the ResNet34. So basically all the parameters should be the same as the previous one you used to train the model. Now I can run this one and take a look. It's only taken just 1 second. And under the hood, it's going to basically subdivide your imagery into smaller pieces, and then you're going to run the inference on smaller pieces. And after, you're going to merge all the result as a single raster. So it's going to save you a lot of time. You don't have to worry about how to put them all together or how to cut them into pieces like other packages out there. It's a lot of steps, but for us, it's just 1 step, 1 function, and then we are done. Once you finish that, you can visualize that. So for this imagery, it's actually just a binary imagery. So if you want to see it, you can, let me run this one here. I can just view GeoAI view raster, okay, and then you can just provide the imagery. So the imagery that we use is, let me see here, it will be this mask path. Okay, so this is the imagery that we generate the output. And then so for the base map, you can provide the test raster path. Oops, so right now let me see here, backend. So something is wrong with my notebook, so I'm going to use maybe volume so that you can show the map. If you run it on Google Colab, it should be fine. So take a look. So now we have this. So we have the detection result. It's not bad. We only trained for a couple epochs, so you can see the result. So this is the binary imagery, black and white. And if you want, you can actually change the black color to 0. So what you need to do is basically shift tab here and then specify the no data to 0, I believe. So no data equal to 0. And let's try this one again. Okay, so not much better. So now we have the buildings detected using this imagery. So the white color represents the building detection result. You can turn it on and off. Like I said, it's not perfect, just a demo, just an example, because I only trained for 20 epochs, and also I only trained using one small satellite area imagery. In reality, usually you want to train on multiple images so that it covers a variety of use cases or different shape, different geometry, buildings. Otherwise, you're going to be only perform well in buildings in kind of similar structure. But at least, like, we only spend a couple minutes, we only get buildings, and that's it. So this is a binary mask. But sometimes you might want to look at the probability, and this is very common in deep learning because you want to adjust the threshold so they can see how confident is the model about the detection. If that's the case, if that's what you want, you can specify the parameter called probability pass. So this one is optional, it's not required. If you don't specify it, it's going to just output just one single raster. So as you can see, we can output the probability, and then we can do the same thing. We can visualize that. So similar here, because I have some issues with IPyLib, that I'm going to use the volume, and we run it. And so now this one, you should see kind of a threshold. So this is not just the binary. So you can see the transition from white to light white. So it's not like fully white. And especially some of these locations. So you can clearly see if the model is not super confident, you are going to basically have a lower probability. And this is where here you don't see the super bright because it's low probability. And so this is optional output. Sometimes if you want to see how confident is the model, you can specify that to get the probability, and then you can make adjustment yourself rather than export the binary data immediately. Lastly, if you want to specify a threshold, like I said, like this image will give you a probability map from 0 to 1, but if you want also to set a threshold, for example, anything greater than 0.3, 0.4, 0.5, you want to set it as buildings, then you can specify this probability threshold. And so for me, I just set 0.3, but you can adjust it. So in that way, it's not using the model like it's so the maximum probability, because sometimes you can be missing a lot of buildings. If that's the case, then you can change this threshold to a much smaller one, and in that case you're going to detect more buildings, but you might get a lot of false positive data. So that's about the inference, right? So going from training the model and then running the inference. But the result that we get, this is pretty much just a raster imagery. So if you're doing some object detection or segmentation, at the end, you might want some vectorized output, vectorized, because you might want to count how many buildings, you might want to count how many swimming pools, how many solar panels, right? So the raster itself doesn't give you the object, individual object. So what you can do is to call, to convert it to vector. So there's a function called orthogonalize. So this is a function that can help you rectangularize the building so that it looks much better. And so the input will be just the raster mask, basically our deep learning model output. And you can convert it to vectorize, and the epsilon is basically the smoothness, how smooth you want your building polygons to be. The larger the number, the more going to be smooth. The smaller number, sometimes if you don't want any smoothing, then you set the epsilon to 0, then it's not going to smooth the result. So for us, it's going to basically count how many image regions and then convert that one to buildings. So in total, we have 1,289 buildings, and that's it. So it's going to convert to raster, from raster to vector. And then you can also call this one line called add geometry properties. That means you want to basically calculate some geometry properties on the vector data. So in that way, you can see how big are those buildings. So let me run this one very quick. It's done. And then the last step is we can visualize the raster and also the vector together. Again, I'm going to use the volume because the IPyLib the problem. So here you should be able to see the raster. So this is the mask. So the white color is what we detected. It's not perfect. Like I said, we only train on one imagery, and the shape, the geometry actually looks quite different because in the training data, we don't really have large buildings. So it doesn't perform super well here. That's what we expected. It can be improved. You can incorporate more training data. So once you have this binary mask, then we can also overlay the vector data, or just visualize the vector data. So take a look, and this is what we have. We also create basically the place maps. The blue color represents smaller buildings, and the yellowish color represents larger buildings. So you can see, right? So once you rectangularize the buildings, it looks pretty decent. Of course, you're going to have some like small tiny buildings, like I said, you can do some post-processing. You can remove some smaller objects. If you already know how big are those buildings, like the common size, then you can remove some of those. But this looks pretty decent. It's like we only spend a couple minutes to train and run the inference. And also for some of the larger buildings, so these actually do not appear in our training data, but the model will still be able to actually detect these buildings. And if you have your mouse, you can see all the attributes, right? So you can see the size, the length, the perimeter, bounding boxes, and also orientation, eccentricity, something like that. So those are some of the geometric properties that has been calculated using the add geometric properties function. So it's pretty straightforward and easy to use. All right, so as I mentioned, if you need to clean up, right, so these are some of the tiny one here. They are not really buildings. You might want to clean it up. So you can set, for example, the size greater than 50 square meters because you have a lot of false positive. Then you can run this one. It's going to get much cleaner results. So we can visualize the result again. So in this way, we only get just relatively larger buildings, but you might miss some buildings as well. As I said, train the model for more epochs and then apply the data to your the model to your data to see how it performs. And so this is the filter result. The last step is to create a split map to compare the result. See here, I have a base map, backend, checkable. So let me see. Back, and it may not work. It's something wrong with my notebook. Yeah, anyway, it doesn't work, so I cannot really show you. Maybe I can restart the kernel and then show you this the speed map. Okay, I have restarted the notebook, so now it works. You can see I have this split map. They can compare the extracted building footprint with the SETA imagery. It's pretty decent, but we didn't spend a lot of time, so you can see how clean the building footprint is. There are some busy buildings. It's normal, like you need to train the models in a bit more epochs, then it should be much better. And also you can see all the shape and geometry, also all the size, the orientation, everything has been calculated. So the output GeoJSON contains all the geometry information that for each building. So it's pretty easy to use. And that's pretty much it. Like I said, if you want to customize this one to your own data, all you need to do pretty much is just here. So if you have the data from the internet, you can specify this and then to download the data. If you don't, then you can just replace these three variables. So the raster path pointing to your data on a local computer, the vector path, so this one can be a vector or can be a raster. Basically, it's the mask or the labels, and then the data you want to test it on. That's it. Then everything else remains the same. But it can be used to detect buildings, trees, or anything as long as you trying to do some image segmentation. You have a binary classes. This is the kind of workflow, right? So again, let me restart from here, and then I can show you the step, right? So import the library, and then download some sample data or use your own data, and then it's going to be training the model. So just one step, or you need to create a training data with the image chip and then train the model, run the inference. Optionally, you can have the probability based map, and then you can do some post-processing and then visualize results. So hopefully this is a much easier workflow. You can get started. So if you're new or you have any questions, you run into any issues, feel free to leave the comments down below. I will make sure to answer every single question, every comment that you have. And I hope this can help you get started. And I have a lot more tutorials here to show you more use cases. I think it's maybe 40 or 50 tutorials already. If you want to learn more, you are also welcome to check out my YouTube channel. So here I have another workshop like 2 hours going through many common use cases, or you can also go to the YouTube channel. So I have all these tutorials one by one showing you how to use it. If you're new to Python, you want to learn how to use Python, then I would recommend you check out my book. The link is also in the video description below, showing you how to get started using Python and open source packages. It's available on Amazon, and also PDF are available on Linkpub. So again, check the link in the video description. And leave any comments if you have any questions, or you have any features or any video tutorial you want to see. I will try my best to record a video for you. Okay, that's all. Thank you very much. I will see you in the next one.